This video is the second in a series about rate equations for A-level chemistry. In the first video, we looked at what we meant by the order of a reaction, and then reactants with partial orders that were 0, 1 and 2, and what the different graphs look like for those. And then in this video, we're going to look at rate equations, rate constants, and also how you can use data tables to work out whether a reactant is 0, first or second order. If you watched the first video in this series, you should know that if a reactant has a partial order of 0, that means that changing the concentration of that reactant won't affect the rate at all. If a reactant has a partial order of 1, then the rate and the concentration of that reactant are directly proportional, and if you double the concentration of that reactant, you will double the rate. And if you have a partial order of 2, then you've got an exponential relationship, and if you double the concentration of that reactant, you would quadruple the rate, or if you triple the concentration of that reactant, you would increase the rate by a factor of 9. There are other partial orders, but as far as we're concerned for A-level, these are the only 3 options we need to worry about. So in each one of these, the rate of the reaction has some kind of relationship with the concentration of the reactants. And we can start to talk about proportionality. So as one gets bigger, the other one gets bigger. So regardless of the partial order, there is proportionality, a relationship between concentration and rate. As I change the concentration, it has an impact on the rate. The rate is affected somehow. But the exact nature of that relationship is going to be different depending on what the partial order is. So we're going to start out with first order because this is just the easiest to understand, because this is directly proportional. I have a nice linear straight line relationship with a constant gradient where that straight line goes through the point that we call the origin 0, 0. And so what this tells me is that whatever I do to the concentration, I do exactly the same thing to the rate. Let's say I start out with a concentration of 2 and I double it to 4. Well, my initial rate of x, and it doesn't matter here what x is, it's just a hypothetical number, will also double to 2x. And then likewise, if I was to quadruple my concentration to 8, I would need to quadruple my rate to 4x. So we can say that these are directly proportional because the rate is a factor of the concentration multiplied by a constant. So here, to get from concentration to rate, I'm multiplying by 0.5x, and I'm always multiplying by 0.5x. And I could even say that my rate is directly proportional to my concentration to the power of 1. Now, that sounds like an extra unnecessary step. In fact, it is, but it's just that when we look at 0 order and second order in just a second, we're going to need that step, and it's kind of easier if we're being consistent. So basically, there's a consistent relationship, a directly proportional relationship between my concentration to the power of 1 and my rate. I'm always multiplying by the same constant to get rate, and that's what we mean when we say that these things are directly proportional. If we then look at second order, again, we've taken our concentration and we've doubled it and then we've quadrupled it, but that's not actually what we've done to the rate. We haven't doubled it and quadrupled it. We've quadrupled it and multiplied it by a factor of 16. So if we want to try and do something involving a constant, which is going to make calculations a lot easier, we need to figure out what rate is actually proportional to. And what it's proportional to is the concentration squared. So you can see now that if I take the concentrations that I've got here and I square them so that I've got 4 and 16 and 64, now I actually do have a directly proportional relationship. To get from 4 to x, I've multiplied by 0.25x. This is a very slow way to write, I'm sorry. And then to get from 16 to 4x, I've also multiplied by 0.25x. And to get from 64 to 16x, I've also multiplied by 0.25x. So we now have a directly proportional relationship. We now have a straight line graph. And all we've done is we've squared the concentration. And this is going to allow us to write an equation that has a constant in it. And that's going to allow us to make predictions about other situations. Now, you might be a little bit unsure about the idea that a 0 order reaction is still proportional because, as you know, if you change the concentration for something that's 0 order, the rate doesn't change. But actually we have still got proportionality here for a particular function of concentration. If we put any concentration to an index of 0, as you know, if you put anything to an index or a power of 0, the answer is 1. So we now actually do have a consistent relationship where we can use a constant and we can write a rate equation. So for any chemical reaction, we can say that the overall rate is going to be proportional to the concentration of each one of the reactants to the power of whatever its partial order is. So if we've got something that's zeroth order, then we're going to raise it to a power of 0. If it's first order, we put it to a power of 1. And if it's second order, then we put it to the power of 2. Now, one thing we should point out here is that those orders, those partial orders that we've been talking about, have nothing to do with the coefficients that are in the chemical symbol equation. And that's different to when you're working out Kc. And I know a lot of people teach this bit right after they've been doing equilibrium constants. And so that can be just like a little stumbling block. So just keep in mind the fact that these partial orders, which here are denoted as m and n, they're going to have to be derived experimentally. You're not going to be able to work them out by looking at a symbol equation. Now, while it's really useful conceptually to be able to say these two things are proportional to each other, in terms of actually doing some maths, we need to know what that x is. Except we're not actually going to call it x, we're going to call it k, because this is chemistry and all the constants are k. So we're now going to say, we're going to take away that little fish sign, that little proportional sign, and we're going to replace it with an equals and a k. So now for any given reaction, rate is going to be equal to a constant that I can work out experimentally, multiplied by the concentration of each one of those reactants raised to the power of the relevant order. Now that K can be affected by a whole bunch of things like ionic strength and surface area and light irradiation, but as far as we're concerned for A level, the one that we're interested in is temperature. So that value of K, that constant for a particular reaction, is only valid for that reaction at that given temperature. And as soon as we change that temperature, we're going to change it. Now we've already mentioned that anything to the power of 0 is in fact 1. So say that n there next to the b was a 0. Well, b to the power of 0 would be 1. And at the point at which it's 1, there's no point in including it in the equation because whatever the concentration of A is times by 1 is still the concentration of A. So anything that is 0 order is not actually going to be included in your rate equation. So just watch out for that. Don't worry if that felt a bit abstract and conceptual and hard to follow. As soon as we put some real numbers back in, this is going to make a lot more sense. So we've got a hypothetical reaction here where we have reactants W, X and Y reacting together to make a product Z. And we've got a rate equation which is rate is K multiplied by the concentration of W multiplied by the concentration of X squared. So we can see looking at this that the reaction is second order with respect to X and it's first order with respect to W. There's, a little imaginary one here that we obviously don't write. So for each of these pairs of reactions, we've got an initial rate that's been calculated experimentally, and then we're changing the concentration of one or more of the reactants and looking to see what the impact will be on the rate and therefore what the new initial rate will be. So for this first line in the table, we're tripling the concentration of W. So we know that the reaction is first order with respect to W, and that means that whatever we do to the concentration of W, that will be reflected by the rate. So if we're going to triple the concentration, then we're also going to triple the rate. So our initial rate was 2, and therefore our new initial rate will be 6. So at this point you need to pause the video and just double check that you're confident in writing down both how changing the concentration will affect the rate and what the new initial rate will be. Hopefully you've managed that okay and didn't find it too challenging. So we've already done the first row in the table. So for the second one, we've got X being doubled. And as we can see here in our rate equation, X is second order. So we know that the rate is going to increase by a factor of 4 because it's 2 squared. And then Y doesn't feature in our rate equation at all. It's not there. So we're 0 order and therefore there is no effect on the rate. And Z again doesn't feature in our rate equation, and in fact it will never feature in our rate equation because it's actually the overall product. So again, there's no impact on rate. Then we've got W being halved. So because W is first order, if we halve the concentration, we're going to halve the rate. So we've got divided by 2. And then we start to stack things together. So hopefully you were able to figure out that if we doubled the concentration of W, that would double the rate. And if we doubled the concentration of X, that would quadruple the rate. So overall, we've increased the rate by a factor of 8. And then if we double the concentration of W, but we halve the concentration of X, because X is second order, we're going to divide by 4. So overall, we're dividing the rate by 2. So now we can use that initial rate data together with these effects on rates to work out some new initial rates. And hopefully you've managed to get these numbers. So once we have that rate equation and some data, we can calculate a value for k. But you might be wondering, what are the units going to be for k? Well, just like the equilibrium constants and all the other constants that we meet in chemistry, the units for k are going to change depending on the reaction we're doing. So if you think about it, the units for rate are going to be moles per decimeter cubed per second, because we're looking at a change in concentration divided by time. And then the units for concentration are going to be moles per decimeter cubed. But the thing is that sometimes the right-hand side of this equation is going to have just the concentration of one reactant, and sometimes it'll have two, and sometimes it'll have three, and one of them second order. And so we're doing a slightly different division each time. And so the units for k are going to depend on how many reactants feature in the rate equation and what order those reactants are. Before we get any further, just quickly pause the video and write down what you think the equation is going to be if we rearrange this to make k the subject. So hopefully you managed that without too much difficulty. K is going to be rate divided, in this case, by the concentration of A squared, because A was second order, multiplied by the concentration of B. So we're now going to look at three different rate equations and what the units for k would be in each case. So we've got one reaction where A and B are both first order, one where A is second order, and then finally we've got one where B is zeroth order and it doesn't even feature in the rate equation. So I can quickly rearrange these to make k the subject, because conceptually it's going to be easier for us to work out what the units are if the equation is in the right format. So in each case I've got k is the rate of reaction divided by, and then the concentrations of A and B to the relevant powers. So if we remember that the units for rate are going to be moles per decimeter cubed per second, and the units for concentration are going to be moles per decimeter cubed, then for our first one we get moles per decimeter cubed per second divided by moles per decimeter cubed times moles per decimeter cubed. So I've just written it as a squared to save me some space. Now all of the moles can cancel each other out, and all the decimeters can cancel each other out. So what I'm left with is moles to the -1, decimeters cubed, seconds to the -1. Now what you're going to find is that for this k, for our rate constant, your moles, if they're there, are going to be a negative power. Your decimeters, if they're there, are going to be a positive power with a factor of 3. And then you're always going to have seconds to the -1 on the end. So say it would be conceivable to have moles to the -5, and then you would have decimeters to the 15. Okay, they're always going to have that 1 to 3 ratio because they've come from moles per decimeter cubed in the first place. Then if I look at my second question, because I've got an additional concentration term that I'm dividing by, I've got moles to the -2, decimeters to the 6. And just in case you're wondering about what I just said, moles if they're there, if you've only got one reactant in your rate equation, then actually your units for k are just going to be seconds to the -1, because the moles per decimeter cubed from the rate and the moles per decimeter cubed from the concentration cancel each other out. So we're now going to start looking at some exam questions. Now, I've never actually seen an exam question that just asked you to explain what we mean by first or second order. What's far more normal is that they give you a bunch of data and they ask you to work out whether something is first or second order. And then you might be asked to just write that information down, or you might be asked to deduce the full rate equation, or even to do that and then to use it in some further calculations. Now this can seem a little bit intimidating because there are some calculations involved, but actually there's a very straightforward systematic method to it, and once you know that method and you're confident and fluent with it, actually these questions aren't that bad at all. So in each instance you're going to be given some data from some experiments, and the first thing you're doing is you're looking for a pair of experiments where only one thing has changed, only one reactant has had its concentration changed. This is proper scientific method stuff. If we change two things at once, we can't possibly work out why something has changed. So if I look at these three experiments that are here, I can immediately see that experiment 1 and 2 have the same concentration of B. So if they have the same concentration of B, only A has been changed, and by looking at A, I can figure out what order this reaction is with respect to A. So if you look, the initial concentration of A has increased from 0.12 to 0.36, so it's tripled. Now, remember, before you do any working out, any calculations, this is multiple choice. Either it's going to be zero order and the rate is not going to change, or it's going to be first order and the rate is also going to triple, or it's going to be second order and the rate is going to increase by a factor of 9. And those are my only 3 options. So don't get in a big panic, particularly if you can't figure out which way round to use the rate data and which one goes on top. Those are your 3 options. So if you can't do a division, just take your initial rate. Has it changed? Yes, it's changed, so it's not zero order. Has it tripled? Has it gone up by a factor of 9? Now, if you are going to do the calculation properly, 1.89 times 10 to the minus 3 divided by 2.10 times 10 to the minus 4 is 9. So what is it? It's second order. This reaction is second order with respect to A. So in our rate equation, we're going to have the concentration of A, remembering those square brackets, and that's going to be to the power of 2 because it's second order. So here's where things start to get a little bit tricky. I need to work out what the partial order with respect to B is. But in order to do that, I need a pair of experiments where B changes and nothing else does. Well, here's B changing, but unfortunately, the concentration of A is also doubling. So what I need to do is come up with a way I can partition the change in these rates so that I know what's down to A and what do I have to blame on B. So I'm going to invent a 4th experiment. And in this 4th experiment, we're going to have the concentration of A changing just like it would do from 2 to 3, but the concentration of B we're going to keep the same. And I can work out what the rate should be for this experiment because I know that we're second order with respect to A. So we're going to look at experiment 2 and my new experiment 4 that I've just kind of invented. So between these, I know that the concentration of A has doubled from 0.36 to 0.72. And because this is second order with respect to A, that means that the rate should quadruple. So if I take 1.89 from up here times 10 to the minus 3 and I multiply it by 4, I get a rate of 7.56 times 10 to the minus 3. So that's what the rate would be if the concentration of B hadn't changed. It's also what the rate would be if B was 0th order, because remember, if B were 0th order, it wouldn't matter that I changed the concentration, the rate wouldn't change either. What I can now do is use this experiment 4 that I've created and worked out what the rate would be with experiment 3 to work out my partial order for A. So now as I go from experiment 4 to experiment 3, my concentration of A doesn't change and my concentration of B halves. And so if I look at my rate going from 4 to 3, I find that my rate also halves. And so that tells me that my reaction is first order with respect to B. Now, one final thing, the question actually says that I need to deduce the rate equation. So this is going to be rate is K multiplied by the concentration of A to the power of 2 because it's second order with respect to A, and then multiplied by the concentration of B, and we don't need to write an index because it's first order with respect to B and you never write an index of 1. Hopefully you followed that, but this is definitely one of these things where just the more practice you do, the better. It's not that hard, but it's just something that you really need to become fluent in. So we're going to look at one more example just to make sure you're feeling really happy with this. So this time we've got E and F instead of A and B. And again, I'm going to start out looking for a pair of experiments where the concentration of one reactant is changing, but the other one is staying the same. So if I look at experiment 1 and 2, I can see that the concentration of F remains constant, but the concentration of E is increasing by a factor of 3. So remember, this is multiple choice. It's either going to be 0 order, first order, or second order. So I know even before I touch my calculator that either the rate doesn't change, well, it does, or it's going to increase by a factor of 3, or it's going to increase by a factor of 9. So if I put these numbers into my calculator, I can see that 0.42 is a ninth of 3.78, and therefore we're increasing by a factor of 9. So this means that the reaction is second order with respect to E. So now I can look at F, and again, I've got the same problem that I had before. I've got some experiments where the concentration of F changes, but the concentration of E also changes. So I need to come up with my imaginary fourth experiment where I control for this and partition up the variation in rate again.
So here in my hypothetical fourth experiment, we're allowing the concentration of E to change, but we're keeping the concentration of F the same. So because I know that this reaction is second order with respect to E, as I double the concentration, we expect that the rate should increase by 2 squared. So we would expect the rate to go up by 4, which is also what would happen in reaction 3 if F were 0th order. So having calculated a rate for my hypothetical made-up experiment 4, I can now look at it together with experiment 3 and find out what order F actually is. So as I look from experiment 4 to experiment 3, the concentration of F has halved, and then if I look at the rate of experiment 4 versus the initial rate of experiment 3, I can see that that has also halved. And so we can see that this reaction is first order with respect to F. And therefore I can put this together in a rate equation of the form rate equals rate constant K multiplied by the concentration of E squared, because E was second order, multiplied by the concentration of F.
Hopefully you're now feeling more confident in constructing rate equations and also in working out partial orders of reaction based on data tables. Hopefully that was helpful. This is the second video in a series of 4, so don't forget to subscribe so that you get access to the rest of them.